I want to use the tool to study the effects of various green infrastructure options that are becoming more and more popular and promulgated in the drainage engineering literature. So not only are we integrating hydrology and hydraulics, we are also integrating some discussion of water quality. Okay, I've got the recorder on, so I shall begin, and I'm going to share my screen. Let's see, what should I keep I'll leave this here so you see my hand moving around. It might be somewhat disturbing. Don't worry, you're protected by your computer screen. As long as your virus scanner is working, you're good to go. Just kidding. Well, not kidding. I'm just, okay, so there's all my dirty mail. There's that. Okay, so today I don't have a prepared deal just yet. I think I was, yeah, this is as far as I had gotten today, because I was going to study the constituent transport. And I initially thought that would be really simple, because how hard could it be? After all, it's a computer program with a graphical user interface. Turns out that was a bad assumption on my part, and so I will freely share that with you. So before I get into the specifics of the pollutant transport, see, I don't need to restart this. I will just dismiss it. I want to return to the technical manual, and what we did last time. Oh, this thing is going to be really annoying all night. Okay, go away. There you go. Gone. Last time we looked at other runoff methods, and what I presented to you was runoff coefficient, or a variation of the rational method, curve number method, and I mentioned the unit hydrograph approach. The other way our computer program generates runoff is by computing infiltration and the volume of water that's left over in a computational time step, one of our delta T's, if you will, after that infiltration is what becomes available for runoff. And so the methods that are employed in the program, see if it's, oh, it's going to do one page at a time because it's a stupid computer. Let me make this a little bit bigger. One of them is Horton's method. It's ironic that the first sentence of the description of Horton's method says it's empirical in nature, because that statement tends to make analysts dismiss it. While it does have aspects of empiricism, the asymptotic infiltration rate and the initial infiltration rate are directly correlated to soil physics. And if you actually have soil physics information, an analyst can make very good estimates of F sub 0 and F infinity. The decay coefficient, that is somewhat less easy to infer, but not unrealistic. So while they say it's empirical, I totally claim that Horton's equation captures soil physics every bit as well as Green-Amped or Richard's equation. The asymptotic infiltration capacity into the soil in my opinion, is well approximated by the saturated hydraulic conductivity of soil. And the initial infiltration capacity into soil is going to be that hydraulic conductivity with an adjustment for the initial soil suction, which again you can look up or compute using methods of soil physics. The decay constant is not quite as obvious in most instances. That would be subjective on the analyst's opinion of how long it takes for the initial suction capacity to be satisfied. Although conceivably you could compute that using F0 as your infiltration rate and determine how long it takes to use up the soil moisture deficit. That'll be on the order of minutes to hours, and you substitute that value into this expression to estimate a decay coefficient. So I maintain that all the parts of Horton's equation are inferable from soil descriptions, or if you're lucky, field measurements. So perhaps you recall Horton's method from your hydrology class, and the curve here, this decaying exponential, represents the infiltration capacity based on Horton's equation, and these bars of rainfall represent incremental rainfall volumes expressed as rainfall rate over some time step, and the portion of those bars that exceeds the infiltration capacity predicted by Horton's equation, those are the portions that become available for runoff. And when we draw a picture, it's really quite easy to draw. Computationally, determining these shaded areas and when they occur is straightforward, but not easy. And what we're often interested in is the area under the infiltration curve as time elapses, because that area represents the volume of water that's lost and stored in the soil. Expressed here as an integral, we can approximate the integral using numerical methods. And then the next enhancement of Horton's method is when the infiltration stops, you can think of a drying period occurs when the actual infiltration rate tends back towards the initial rate, tends away from the asymptotic rate. And so as drying occurs, the soil recovers the ability to store water. And that's Horton's method, and the inputs that we need are the initial rate, asymptotic rate, and the decay rate. And then if we're going to do recovery, the recovery period. I'll skip forward here. It describes the computational scheme, and what is important for us is the parameter inputs. So I just happen to have a swim model up and running, not a very elaborate one. One watershed, shaped like a kite, draining to one node, draining through one pipe, going to an outfall, and we have rain gauge, which is generating a very silly looking storm. Hour 0 to 1, nothing. At hour 1, produces 1 inch an hour up to hour 6 and then stops. So there's nothing at all special about that. This was how I was reverse engineering the transport component, and I introduced a constituent called yucky stuff, spelled Y-U-C-K-Y. I think that's how you spell yucky, because all it is a name. Let's look at our subcatchment. Currently, the infiltration is set up as Horton's method, and the maximum rate is that initial rate. That's at F sub 0. So this one's set at 3 inches per hour. The minimum, the asymptotic value is set at 0.5 inches per hour. The decay constant is reciprocal hours. And let's see, I have a 9-hour simulation. I'm going to go ahead and change this to something a little bit more energetic. So this will make a steep drop-off curve and get to that 0.5 inches per hour. And I think I have everything set at 100% impervious, but let me change that. I'll make everything pervious. Well, let me actually leave it at 100 and we'll run it once so you can see what the output looks like. So we're just going to look at the hydraulics. The water quality part isn't that is for a different consideration. So let's look at how much water comes off the watershed and makes it to junction 2. So I will change that to total inflow. Press the okie dokie button. So here's what's coming into the junction. The watershed area is 5 acres, and I have set the parameters so that essentially right now it has a runoff coefficient of 1. And so 1 inch per hour over 5 acres should produce 1.008 times 5 cubic feet per second. Basically 5 cubic feet a second. And sure enough, it does it. It comes up to 5 and stays there until the end of the storm and then drops off rather quickly. That's an artificially constructed hydrograph, but again, because currently I'm reverse engineering behavior, I wanted to do that. Now let's change the infiltration behavior of the watershed. So if I activate Horton's model, essentially switch from 100% impervious to 100% pervious, so completely flips everything. Initial infiltration rate is 3 inches per hour. So I would expect that we won't make it up to 5 CFS in the first few hours. I would expect this to kind of have almost a curve like this and look like a shark fin. I know that's a very technical word there. So everyone knows what a shark fin looks like, right? You're all being kind to me tonight. Thank you. So percent impervious, if I set that to 0, that means everything becomes pervious. I'll see what happens if I can leave Manning's N on the permeable set to 0. I don't know if this will actually work, but there's an easy way to find out. What's the easy way to find out? Click on the lightning bolt. Well, that was amazingly quick. So sure enough, I got the shark fin. Actually, I got much more of a shark fin than I expected. So in our case, it took 1, 2, almost 3 hours for the infiltration capacity to get down to a rate that there was any left over for runoff, and our runoff is now at 2.5 cubic feet per second. So before I move on, the numbers notwithstanding, does the fact that we switch from impermeable to permeable and we have an infiltration component that takes water out of the rainfall signal make sense to you? Does this output trace make sense to you? Not regarding the numerical values. Remember last time it was a square wave starting at 1, going all the way up to 5, and then dropping off at 7. So in this case, we don't get the square wave because the area that used to be under here is all lost to infiltration. And if we modify our hydrology, changing the decay constant, I'll go back up to 5 hours for a time constant. Actually, let me make it the length of the storm. I'll make it 6 hours. So I've changed it from a 1 to a 6. So I think this shark fin will get fatter. So in other words, this point where the cursor is will move to the left, tend towards the 1, and I think it'll get a little taller. One way to find out is to run it, and sure enough, it moved to the left, and oh, it didn't get taller like I thought. So it did move to the left, and then to make it taller, if that's what we expect, that requires that we jack with the minimum infiltration rate. So let me make that half as big, so it should go to something larger than 2.5 at the peak. Run it, choose the OK, shrink it, and indeed changing the asymptotic rate affects how high this goes. All right, so we have reverse engineered that infiltration model. And I personally like the Horton model because it gives me, the modeler, an immense amount of flexibility in describing each of my subcatchments. As long as I can defend my choices of f sub infinity and f sub 0, I like it. In some client situations, they will forbid you to use it because they see the word empirical. They can read too. And that lets us go to another model, which we're moving on to next, which should be see, modified Horton. Oh, the modified Horton, instead of dealing with infiltration rate, uses infiltration volume and then does differencing to compute rate. So it's really the same method. So green amped is the other major infiltration method that is incorporated into the computer program. And see, they're giving it to green and amp 1911. It's actually, green and amp were soil scientists. The actual arithmetic predates them by quite a bit. I have a book from Russia that was translated where this exact picture and the requisite mathematics is presented, and it's from the 1890s. So just like Chekhov used to say in Star Trek, we invented it first in Russia, and then the rest of the world found it. Russia has had to cope with not having computers like we have, and so instead they developed very elaborate mathematics and conformal transformations. And so this particular problem in the Russian book is solved in a phenomenally elegant way from a mathematician's point of view. in that there are two unknown parameters that are related to each other by a logarithmic function, and you can start at one and pretty much graph the solution. Techniques that are essentially lost to time. We don't graph anything anymore unless the computer does it for us, and nothing wrong with that. That makes a lot of sense. So in the gradient model, they model this vertical portion where the cursor is moving up and down represents the soil column at the bottom of your watershed. If we go back to, let's see if I can make my way back to the picture I want. So it represents this soil down here, however long it needs to be. And the only mistake I just did is now I can't remember what page I was at. Pretty close guess. So that's that brown soil column in the prior picture. And the phenomenological model that is approximated, visualize rainfall falling onto a watershed, and then it pools on the land surface, kind of like it did yesterday in, was it yesterday we got the good rains, or day before? One of the two recent days. So it pools right away, and then it starts to soak into the ground. And at some moment after the pooling has begun, the water has infiltrated a distance into the soil, and there are two relatively definable zones. There's the wet zone, and they call non-wetted, wet and dry. And we can define this interface. The simplest expression of a gradient model is to declare the water pressure at the wetting front at atmospheric pressure. And then you can write Darcy's law from this ponding soil interface to the wetting front. And if you recall, Darcy's law is Q is equal to K, the hydraulic conductivity times the area times the hydraulic gradient. The hydraulic gradient in the vertical in this picture, at the top, at the water soil interface, the total head at that position is elevation 0 plus however deep the water is, a couple inches. And then at the wetting front, the total head is minus the distance into the soil, plus 0 for the liquid pressure. And so we take, let's call this depth cap H. We take cap H minus a minus Z, and then divide by Z. So we have cap H plus Z over Z gives us our hydraulic gradient, and that changes with time. And then we have all the pieces that we need to estimate how much water is soaking into the soil. Because this wetting front, we know how fast it's moving. That is determined by that hydraulic gradient and the saturated hydraulic conductivity. So I'm not sure that my verbal explanation is all that clear. I'll dig up the Russian book at some point and translate it for you. My point being is what's going on in the wetting zone is simply Darcy's law is being applied, and the position of the wetting front is being tracked, and it has a velocity that's roughly equivalent to the rate of water soaking into the soil multiplied by the porosity of the soil is how fast this is moving. And that again is a property of soil. And as it infiltrates, we know how much water is lost from the ground surface layer. What's left over becomes the interactive mode. You guys got to pick a word. What's left over after the infiltration is computed becomes?
Runoff.
Very good. Thank you for playing. We know you have a choice in your evenings. Thank you for choosing my boring lectures. Using Darcy's law, we can express a couple of infiltration rates. This is the one I just described in words, which is the initial suction. D is the depth of ponding water above the soil water interface. L sub S is how deep the wetting front has traveled. And if you look at that, that is a hydraulic conductivity, a head divided by a distance. It's Darcy's law with the area term divided out. So this is per area of watershed, if you will. And that gives us an infiltration rate. We're also concerned with the cumulative infiltration because that in its own right is important, because that's actually what gives us the ability to determine what becomes runoff. And we can either directly integrate it or make some observations or some stipulations about the saturation behind and in front of the wetting front. And with that, we can also express the infiltration rate, again, as saturated hydraulic conductivity multiplied by the quantity 1 times this times suction times porosity divided by the quantity that's infiltrated, because the quantity that's infiltrated is directly proportional to the distance that the wetting front has moved. And initially, the infiltration capacity, the computed infiltration capacity will initially equal or exceed the rainfall intensity. So at least for the first few time steps, or fractions of a time step, all the rain that comes in will directly infiltrate. And in a period of time called the time to ponding has to elapse before we actually get a computed infiltration rate and computed infiltration excess, which becomes the runoff. I'll let you read these on your own. The author of this, Lou Rossman, did the best he could to summarize hundreds of pages of theory in as easy a way as he could. And if we look at this chart, this is amount infiltrated, cumulative infiltration depth plotted for infiltration capacity. And until detectable ponding occurs, the infiltration rate is quite high, and then it starts to drop down. Now, I want you to take a look at that curve, just the shape of it. We kind of have a high initial infiltration capacity, and then down here we have what appears to be an asymptotic rate. And I want you to quietly think to yourself, what's the difference between that curve and Horton's curve? And the answer that you may or may not conclude is there is no difference. It's a different set of jargon explaining pretty much the same phenomenological process. The attractiveness of the green-amped method is saturated hydraulic conductivity is a property that can be approximated based on soil textural description, or you can take a sample of soil and put it into a laboratory device and then charge several $100s an hour and get a number. And I'm being unnecessarily cynical there in certain contexts. That's money well spent. But any geotechnical laboratory can recover a saturated hydraulic conductivity for you. The moisture content at complete gravity drainage deficit can be computed using a, what's the device called? I've manufactured them. There's a hanging column permeameter. That's not the right name, but that's close enough. This value is also determinable in a laboratory experiment. And the way those experiments are conducted, you can also get the suction pressure at different values of soil moisture. So everything in that equation except for capital F can, in a circumstance where there's enough financial incentive to do so, can be determined from laboratory analysis of samples, or more commonly from textural descriptions of soil types. The cap F is actually determined as the solution proceeds. You'll notice that cap F appears in two places. That's called an implicit equation, and that can't be simplified any further than that. There's no point. Because of that logarithmic term, you can't isolate the F and put all the other garbage on one side, which is not a big deal. We already know how to do implicit equations. We can guess a value for F, attempt to solve the equation, and Newton's method the sucker to death until we get a value that satisfies it, move to the next time step, do it again, and then that's what goes on inside the program. Like Horton's method, infiltration capacity can be recovered if there's periods of no rainfall. And skipping ahead, it describes the computation scheme. And more important, there's a nice description on parameter estimation. So saturated hydraulic conductivity, again, laboratory study or from textual description, or you can use the data by Lou Rawls et al. I don't know if it was Lou Rawls. I was making a joke. And then the suction head at the wetting front, also determinable either from textural description or laboratory experiments. And then the maximum moisture deficit available. It's essentially the interconnected porosity of the soil. A reasonable approximation, if you have the information, is the wilting point of the soil is going to be pretty close to the maximum soil deficit. And here is a table based on data for 5,000 or 6,000 different soils across the United States, mean values, and then plus or minus 1 standard deviation. So every number of the alphabet is on this table. So there's quite a bit of flexibility in the green-amped method, and it is considered somewhat more defendable than Horton's method because there's the illusion of it being less subjective. And bear in mind, I use the word illusion intentionally, because the difference between a sandy clay and a silty clay is what? Yeah, I don't know either. So I can tell clay from other soils. I can sometimes tell loam and then sand, because I went to school back when you used to stick dirt in your mouth to be able to make a textural description. And now they don't do that because apparently soil is contaminated and will make you silly. But we used to have to take our soil samples and put them on your tongue, and you can feel if it's sand, and you can feel if it's clay. Clay is like really slick and almost soapy tasting. And if you've never had soap in your mouth, then your mother didn't raise you right. And then loam isn't as gritty as sand, but you can detect with your tongue a roughness to it that's not present with clay. I don't suggest that you go to a job interview and say that that's how you contextually describe soil, they'll have a cow nowadays. There's probably a Raspberry Pi program that does it for you. There's some other information here regarding disturbed and undisturbed soils, and urban soils often don't behave like this table suggests, namely because they've never read it. But if I was dealing with an urban soil and had no way to get laboratory data, in the case of porosity, I would choose the lower value in the 1 standard deviation. And in the case of a suction head, I would tend to choose the higher value if indeed it was dry. And then the hydraulic conductivities, they're not presented with a range here, but I would tend to reduce my hydraulic conductivities in urban area to reflect that most urban soils, at least superficially, are unintentionally or intentionally compacted relative to a natural soil. And so you can adjust for that compaction by slightly reducing the hydraulic conductivity, reducing the porosity to the lowest value, and then increasing the suction head proportionately. So if we had a soil science class, we could spend a week on all that. Actually, more than, I guess a week would be a month. We could spend quite a while on that. There is a fair amount of wizard hatness that goes on with soil science when we're using it as a modeling tool. So I will skip the suction head other than mentioning that it can be determined experimentally. And oh, actually, this actually has the wilting point. Well, that's cool. I came up with that all by myself, and turns out in 1973 somebody else had the same idea. Well, bright minds think alike, right? Wilting points are relatively available from your soil science or natural resources friends. And if you don't have any, you should make some. So that is the other model of infiltration. Let's keep this picture in mind, and we're going to switch infiltration models in the prototype model that I'm here learning to reverse engineer things. And I think I could change infiltration method by going to green amped. And what was our hydraulic conductivity before? I think it was 0.25. So I'll use the same hydraulic conductivity, but I will jack up my, see, I got an inch an hour coming in, so I will say fraction. I will make a soil that doesn't exist. We'll make it an aerogel. And let's see what that does. So what I've just done is I've made a soil that is very dry, and 90% of its porosity, which actually of the soil porosity and initial moisture content is vacant. Hydraulic conductivity is a 1/4 inch an hour, which is the same as the asymptotic rate in Horton's method in the prior case. Suction head is a bit low for a soil of those properties, but we'll go with it. And I'm trying to see where I enter the porosity. Huh. Must be there somewhere else. And so here's our old shark fin, and let's see what happens when we change infiltration models. So I expect stuff to move around because it's pretty unlikely that I made correct guesses and can replicate this. But the green amped one is gonna have similar waveform appearance. The numbers will probably be different, and I think this vertical line will shift a bit to the right. Ooh, quite a bit more to the right than I expected. So, and again, just like with Horton's method, we could adjust parameters and recover a waveform that's quite similar. And that's why I maintain that they are essentially the same method. Let's see, my suction head was too big, so let's go with 1/2 inch. So let me think of what that's going to do. So I think this will square up a little bit more. By changing this suction head, I'm losing this storage capacity up here. Let's see if I'm right. Sweet. Okay, so it basically is the same model. So if you're working for a client and they're arguing that your Horton's method is BS, switch to green amped. You may have to jack around a little bit to recover your Horton parameters, and odds are the numerical values you use will be defendable from the literature. So at this point, as far as the per subcatchment hydrology is concerned, we've now explored the two ways of generating runoff. A runoff generation method, such as runoff coefficients or NRCS curve number method, and infiltration excess, in our case, either Horton or green amped or modifications of the two are available to us. So if you remember your other hydrology programs, there's only a few more infiltration models that are commonly available. So we can capture most of the hydrologic response that we need using the limited tools we have here. The next topic I was interested in was how we manage water quality. And as I started to read, I was a little bit, I won't say annoyed, I had greater expectations. And the water quality that it can mimic are essentially conservative components with first order decay. So I guess that's not conservative, but it can't do reactions. And rather than being mad at them, I got to thinking back of the history of this particular program, and they probably never anticipated anybody wanting to do reactive transport. So the best way to consider it is it's a way to introduce constituents that are either conservative, like total suspended solids mass conservative, or constituents that may have some first order decay, so radioactive dirt, or maybe biochemical oxygen demand, but I think that would be really pushing this tool. And then as I did further reading, I was even more frustrated in that there is actually no documentation in the user manual that I could find that explains how to use the water quality tracking feature. But there's a applications manual that does. And so here's my reading of that. In our data browser, we have objects called, we have a class of objects called quality. And one of the quality objects is pollutants. Another one is called land uses. And so with that, I started to not attempt to replicate their example because I didn't want to replicate their example. I wanted to slowly understand how this program works. And so let me share that with you. So here's the base model. All I was trying to do was figure out how to model a constituent that goes by the rather clever name of yucky stuff. And in the interface, there's this section here called quality. And in the quality, we have pollutants and land uses. So in pollutants, if I click on yucky stuff, I can give the pollutant a name, but let's change its name. Somebody pick a name for this pollutant. Fish food. Spelled wrong. So let's say fish food is a pollutant that we're concerned with. And the units are always mass densities. So milligrams per liter, micrograms per liter, I guess that's pounds per liter, a mass density. So the units will make all my environmental engineering colleagues very angry. The units are essentially dimensionless. They only represent a ratio to a volume, and you have to use external calculations like area and flow rate to determine that volume to recover actual masses. There's nothing unusual about that. That is how most contaminant transport models are managed. It's a lot easier to work in the mass density world than it is to actually compute masses, because then you have to keep track of volumes everywhere, and it gets complicated fast. And I'm going to set the concentration of fish food in the rain to 0. The concentration of fish food in groundwater is 0. Inflow infiltration is 0. DWF, I forget what the acronym means. Dry weather flows. So think of that as sewage flows. And the initial concentration is set to 0. I have a decay coefficient of 9, which I will return that to 0. Okay, so we now have a pollutant named fish food that starts out life in our system as 0 everywhere, and when the rainfall comes in, that doesn't bring any fish food into it. So fish food isn't going to be very interesting right now. If I run my simulation, my fish food concentration, if I'm was to go ahead and plot it, I should get a flat line at 0. And of course, I still have buildup. I was expecting a flat line, but there's another part of quality, which is land use. So I've declared a land use called type 1 because I have absolutely no creativity in naming. It's intended that you put stuff like residential subdivisions, single family houses, light industrial, major prison area, stuff like that for the land use name, and then you can describe it. And this is just a character string. Then they have something called a buildup function. And what the buildup function is see if I can get the right. Is it this one? Oh wait, it was a website. Gotta get to the website. Wrong one. fire dog. Where is my Firefox? There we go. See if I can find it. I had it. There we go. I think they had a drawing of a buildup function. So this is classic EPA documentation. Everyone else, they depend on other people to do it for them, and you have to do a lot of reading in multiple places. If I can get back here, okay, runoff water quality and info swim, which isn't even swim. They had a picture of the different, so this is right out of the swim manual, but that's useless. They have a nice picture of what the different functions look like, if I can find it. Maybe I'm hallucinating. There we go. So the buildup function is defined as the following. Pollutant buildup that accumulates within a land use category is normalized as mass per unit subcatchment area or unit curb length. Mass is expressed in pounds or kilograms. The amount of buildup is a function of the number of preceding dry weather days and is computed using one of the following functions. So frankly, that is an asinine way to do it, but that's the way the program works. So we have a power function model, an exponential model, a saturation model. And we're going to supply the number of days prior to our rainfall event that buildup accumulates, and then it will accumulate according to these values C1 and C2. In the case of an exponential model, C1 is the most that can build up, and then C2 is the buildup rate constant. If C2 e to the minus 0 is 1, the bigger C2 is, the faster you get to the C1 value. That's the exponential. There's a few other models. You can read those at your leisure. So I've chosen the exponential model. I'm going to set the buildup maximum of 10. I'll make my rate constant 0.5. I'm going to allow 5 or 6 days antecedent moisture conditions. So that's 10 rate constants. So I should get my max buildup to 10 before wash-off occurs. Now the wash-off function is a function that describes how that built-up material is washed off the watershed. Again, in my opinion, a somewhat asinine way to do it, but in deference to the original creators of the tool, for what they were trying to achieve, this makes complete sense. And so we have a couple of different wash-off functions. Rating curve, so it's a coefficient multiplied by the amount of overland flow coming off the watershed raised to some exponent. Rating curve makes a lot of sense to me. Naturally, I chose exponential. So again, there is a coefficient times flow rate per unit area raised to some power, multiplied by how much pollutant is available to wash off. So I kind of like that model. So visualize, if you will, the pollutant is a bunch of ping pong balls that have collected on our watershed. A lot of ping pong balls, a whole bunch, enough for all the ping pong players in China to play simultaneously for weeks and not have to go chasing after a ball that they miss. Okay, a lot of ping pong balls. And it starts to rain on our watershed and the water runs off. And as it runs off, it floats a few ping pong balls per minute with it. So initially, when you have a lot of ping pong balls, our value B is pretty big. And even if the Q to the C2 value is kind of small, because there's a lot of ping pong balls available to wash off, they come off pretty easy. as we wash off, if we get near the end of it and we're almost out of ping pong balls, the last ping pong ball takes a lot more wash off than the first one. It's kind of like when you have your kid clean a room. If you've ever watched kids clean rooms, they take their messy room and they clean it up a little bit and they shove all the mess into a corner. So 85% of the room is clean. It's that 15% in the corner that drives you nuts. Now the smarter ones move that 15% to underneath the bed or somewhere in the back of the closet and everybody's happy. But the last few percent, it's harder to clean a place up that's already almost clean than it is to clean a place up that's really filthy. Because if it's filthy, the first few things you take out of the way makes it look a whole lot better. But when it's almost completely clean, the last few things you barely notice that they're gone. So that's what this exponential function is trying to mathematically represent. So I've set the coefficient at 2, which is the C1, and then the exponent is 2, which is the C2, and then B is what's ever built up. I just pulled those numbers out of my datum. I read somewhere that in wash-off for solid constituents like soil particles, based on some laboratory experiments done many years ago, the exponent is pretty close to 2. So that's good enough for me. Some arcane reference from the 1960s says it's 2. And since I don't really know what they do, that works for me. Okay, let me modify my buildup function for the time being. Let's run the max buildup to 0. Hopefully it will allow that. Okay, so what that means is there's no fish food accumulating on our watershed during the dry phase. And if we go to options, in dates, I have 10 days antecedent dry days. So there's 10 days of solids buildup before my little storm here. And I've just set things that I should get a flat line coming out unless something else is wrong. So there we go. No pollutants built up, nothing to wash out. There is no fish food in the link. But if our land use property changes, well, let's say the maximum buildup can get to be 10 pounds per unit of normalizer variable. So this is where I find these particular models rather confusing, is the units of the different things are changing a lot. And it's not obvious when you first start to access the program that that's happening. And so now I've got it such that I have accumulated fish food on my watershed. When my rain comes, it starts to wash it off, and we get to a point where there's almost 40 milligrams per liter of fish food, and then it starts to decline as it's getting washed off. And I'm sure somewhere in the program, in the report, it will give me actual total masses involved. So my initial buildup is almost 50 pounds of fish food. That's a lot of fish food on my 5-acre watershed. I think it would stink. There was 2 pounds of surface buildup. I'll have to read more of what that is. And then when I finally generate runoff, I wash off 49.327 pounds over the course of my simulation, which is why I get almost back to 0 here. So at this point, we have now reverse engineered a way to simulate a water quality of materials being washed off our watershed. We also can modify fish food. If we go to the coast where everyone knows that flying fish come down with the rainfall, we could put in a rainfall concentration, and where I think this would be valuable is that it could be used as a way to trace flow proportions. I don't think they ever built the program with that in mind, but this would be a way to be able to source water from different parts of a watershed. So a complicated watershed model, that could be somewhat handy. So what this should do is we've set the fish food in rainfall up to 10. So instead of coming back down here to 0, this should come to 10 at 7 and then start to decline, unless I'm wrong. So we have rainfall bringing in fish food plus what's washed off. Then it comes back down. Most of the wash off has been accounted for, and there's still this little bit of 10, and then the rain stops and the fish food washes out. So that was actually all I wanted to do today, was the steps of reverse engineering. We've reverse engineered the infiltration choices, and we've reverse engineered at least a few steps in how constituents are modeled. Our next step in the water quality, which we won't do tonight, is to examine what effect infiltration has on the water quality, because the fish food should also be soaking into the ground as well as running off, and that should have an effect on the water quality. We can experiment with that real quick, just last thing this evening. If we change the suction head to 3, so that's going to produce less runoff, less net runoff, and let's see what effect that has on the, wanted to move that, I didn't want to resize it, on fish food. So there's my total inflow. So this is going to get more shark fin-like. Oh, interesting. So it does have an effect on the fish food concentration. Not what I would have expected, but that's how modeling is. A lot of our intuition kind of has to go out the door. If the model produces absurd results based on your intuition, the model's probably wrong, or you've conceptualized it wrong. So instead of the initial rise, all the fish food that would have appeared here, because the infiltration takes water away, so it affects the wash-off function considerably. And at the end of the storm sequence, what would have been the 10, we still have quite a bit of mass before everything drops off and washes out. We'll explore that more next time. I have an old field project I did 20 some odd years ago, not in swim, predates swim. Swim may not even be able to simulate it, but I will attempt to assemble that data and at least get a lot of it put together and make a nice homework assignment so that you all get to practice with this. If you develop an ability to use swim as a water quality modeling tool, that's going to give you a pretty competitive edge over most users of swim. The water quality was added late in its history, and don't think a lot of folks are terribly aware of what it can, and more importantly, what it can't do. I don't think it can model reactions. We could make the fish food decay, because everyone knows that fish food does decay, right? I'm just going to pull a number. Let's see, decay coefficient reciprocal days. I think if it's big, it decays fast. can barely see the effect of decay. So maybe it's small. No, I think big decays fast. So we actually have, in terms of the total mass of fish food entering the system and leaving, they're not the same because we've enabled first order decay to occur during the simulation. Let me make it really big. And yeah, we get fairly dramatic decay. Now, a decay rate of 99 reciprocal days is absurd. But that gives us the ability to reverse engineer the tool. So in terms of our integrated hydrology and hydraulics, we've now at least explored the necessary knobs, if you will, on the tool to be able to convert rainfall into runoff at the subcatchment level, introduce pollutants of some type at the subcatchment level, and we already know now how to route it and get our hydraulic components built. So we pretty much have most of the tools we would need to do green infrastructure type model assessments, and that's where we're headed to next. The other thing we could do is we could have just as well turned fish food into salinity, and I think we actually can set a value. I'll have to read about that, but I think we can set a value at the outfall of the constituent and use it to model a saltwater freshwater interface in a riverine system. Again, that's something I don't think they originally envisioned the program would be used for, but I think that can be approximated. I'll read how to do that. So for the time being, we now can model hydrology. We can take that hydrology and put it into a hydraulic network, which we could not effectively do in something like HEC-HMS. HEC-HMS isn't built to do that. HEC-HMS doesn't do sewers for shit. So for urban areas, we have that capability, and we have a little bit of ability to keep track of water quality, primarily to test options to control water quality in stormwater, which is to some extent always been a big deal, but certainly lately it's been a bigger deal, and I think we can expect in the near future a lot of emphasis on water quality management of stormwater, given the new federal administration and its focus on green, everything being spray painted green. So this is pretty timely that we're teaching ourselves how to do this. And I sound a little cynical in that. I'm actually not. It's generally good engineering to control the water quality of your stormwater. You get a lot of other benefits. But if that's what it takes to justify doing good engineering, I'm cool with that. And you should be too. That's all I have for tonight. And thank you for your attention and not completely passing out. And thank you for saying runoff when I did the one interactive component. I will, this particular model, I don't have the file saved in any way that you guys can get at it. I will work on putting that together and getting a write-up for it. Because if nothing else, at the end of this semester and you go out and you get a job, and at some point in the future, the need to do swim and water quality arises, you'll at least be able to go back to that and save a few hours at the beginning of the reverse engineering part. unless there is actual proper documentation somewhere that I've completely missed. And that's quite possible that I've missed it. But with this swim5.org and openswim.org, you can learn a lot. This dude right here is actually one of the original programmers of Swim. He didn't program the interface. That was done by a fellow named Lou Rossman, but he actually wrote the original Fortran code that got converted into C++, which is what we see here. And I've served as his driver once a few years ago. He's an interesting fellow. So if we ever were to get stuck, we can certainly, you could contact him through one of these website deal things, and he's actually fairly responsive. The weirder the question, the faster he'll get an answer to you. Okay, that's it. Any questions? Y'all ready to go have dinner and watch TV and go to sleep? I know Richard's ready to go to sleep. He's got the bed right behind him. All he's got to do is turn off the computer and jump back into bed and turn out the light. Okay, well then I will see you guys on Monday and have a great weekend. I have no homework for you over the weekend unless you want some. I think it can wait till we can come up with a meaningful problem. And I will see you on Monday.
Have a good weekend.
Have a good weekend.
All right, you too. Bye-bye.